Welcome viewers to the NPTEL lecture series on the calculus of variations. This is the 17th lecture of the series. In the last lecture, that is in 16th lecture, we allowed discontinuities to occur in the derivative of extremals. So, that we can apply these results to problems appearing in optics, where we considered reflection from a given function y equal to phi x, the functional extremal got reflected at a point C. This extremal joins two points A and B which are given, and C is a point moving on the function y equal to phi x, and the extremal is getting reflected at C. So, it starts from A and it gets reflected from C and joins the point boundary point B. So, here we are supposed to get that point C, so that the functional I gets optimized. So, here also we considered the problem of refraction. So, here in the first case we considered this picture here. So, this is the point A and the point B, these are given points here, and C is a point which is moving on the curve y equal to phi x. And so, this extremal which joins these two given points A and B gets reflected at C. And so, here although y the extremal y is continuous, but its derivative is discontinuous at C. And so, here in the first case, reflection case, both A and B are on the same side of the curve y equal to phi x, and so we use the condition here, this delta I, which is sum of these variations delta I 1 plus delta I 2. We break the integral x 1 to x 2 at x 3, which is the point C x 3 y 3, and so we get this delta I evaluated at the point x 3 minus, that is the left limit, and x 3 plus, those things two values are then equated, and that is the condition 16.3 which we had got in the last lecture. And then we considered this example 16.4, where this f x y is non-zero on the given function of y y equal to phi x. And so, we got the condition here that this 1 plus phi prime y prime over square root 1 plus y prime square at x equal to x 3 minus, that means the left limit, and same thing at the point x 3 the right limit. And so, here if we denote this the tangent at tangent to the curve y equal to phi x at C makes the angle alpha, and tangents at the extremals at the point C, because those at the point C we will have two tangents, that is why the derivative is discontinuous at C. So, denoting those left tangent and right tangent as tan beta 1 and tan beta 2. So, that the angles made by those tangents at the on the x axis as beta 1 and beta 2. So, we denote them like this: tan alpha is phi prime at x 3, phi is assumed to be smooth. So, that derivative at x 3 exists, and tan beta 1 is y prime at x 3 minus, and tan beta 2 is y prime at x 3 plus. So, we got this condition here, since these two angles are here, beta 1 is like this and beta 2 is like this. So, we get here minus sign in this sec beta 1 here, and then multiplying by cos beta 1 on the left side and cos beta 2 on the right hand side, we get here this minus cos of alpha minus beta 1 equal to cos of alpha minus beta 2. So, this is pi minus alpha minus beta 1 equal to alpha minus beta 2. So, these are the angles at the point here, and so the incident angle, because alpha minus beta 2 is this angle which is made to the tangent by the tangent on the curve by the tangent on the extremal. Similarly, you have alpha minus beta 2 gives us this angle. So, pi minus alpha minus beta 1 will be the other angle, which is the incident angle. So, we get here the famous law of reflection, that is the angle at the incident is same thing as angle of the incident is equal to angle of the reflection. Now, in the case we have refraction, so then the figure is explained here. In the case of refraction, the point A is on one side and the point B is on the other side of the function y equal to phi x. And so, here we have different mediums, the light ray is travelling from one medium to another, and obviously, then the function the integrand will be discontinuous at C. So, we take two different functions f 1 and f 2 there. So, as integrand, and although y may also have discontinuities of its derivative at C, and f also has discontinuities at the point C. So, we break this integral again in two parts, x 1 to x 3 and x 3 to x 2. Here on first we have f 1 and on the second we have f 2, and then proceeding in the same manner we get here delta I y. Finally, we get that delta I y that should be equated to 0, the first variation must be 0, and therefore, it leads to the condition that f plus phi prime minus y prime f y prime evaluated at x 3 minus, that is the left limit, is equal to the same value of the same thing at x 3 plus. So, that is what was obtained in the last lecture as 16.3. And so, here if I y is taken as x 1 to x 2 f x y square root of 1 plus y prime square dx, then we will have two different functions f 1 and f 2 there. And so, we get here in the case refraction, we get two different functions f 1 and f 2 there, and so we get this condition here. And so, in this example we have f as f 1 on the left side of the curve and f 2 on the right side of the curve y equal to phi x. So, we get this condition here, and denoting those angles as we had denoted earlier. So, we get here that cosine of, now actually beta 1 and beta 2 both are on the same side in the refraction case. Here this tangent to this will come here like this, that is beta 1, and like this it will come somewhere here beta 2. So, they are on the same side here, and alpha is like this, and so we get both the signs will be same here, and we get in this case cos of alpha minus beta 1 over cos of alpha minus beta 2, and if these functions f 1 f 2 are 1 over v 1 and 1 over v 2 respectively, where these v 1 and v 2 are the velocities of the light ray in those two different mediums, and then we get this thing. And since for in the law of refraction the angles are measured from the vertical line like this. So, angles are measured, we are measuring angle at the tangent, whereas if we need to measure those angles from the vertical one, and therefore, we take pi by 2 minus of these angles. So, we get sine of pi by 2 minus alpha minus beta 1 upon sine of pi by 2 minus alpha minus beta 2 equal to v 1 upon v 2. And so, what it says that the sines of the angles, the ratio of the sines of the angles of at the point of refraction, we get the ratios of those this ratios of the sines of those angles must be equal to the ratio of the velocities of the particle in the different mediums. And so, this is what is known as famous law of Snell's law of refraction, that is what is obtained in this analysis. Now, here not only the discontinuities in the derivative of an extremal can occur only in reflection or refraction, there can be instances where these may occur in other instances also, like if you consider this example. So, let us call it 17.1 now. So, this is I y equal to integral 0 to 1 y prime square 2 minus y prime whole square dx, and here this y 0 equal to 0 and y 1 equal to 1. So, here situation is obviously I y is greater than equal to 0, and there is no finite maximum there is no finite maximum because y prime can take as large value as possible, and so only finite minimum is possible. So, here extremal value is actually minimal value, and that is I y equal to 0, that is I y equal to 0, and which occurs if y prime equal to 0 or y prime equal to 2. So, that is on y equal to C 1 or on y equal to 2 x plus C 2. And so, here what we have is the following. This is x y axis, and here this point A is 0 0 and B is 1 1, and so here, and let us say this is half. So, here of course, y equal to x is the line here joining here, which is a straight line here, because this functional here the extremals are straight lines. Okay. So, we have a line joining these 2 points, that is y equal to x, but on that y prime is not 0 nor y prime equal to 2. So, this I y will not be 0 for that. So, here what should happen, that we should allow only y equal to some constant, that is horizontal line, and then y prime equal to 2. So, that we have this line like this, and so we can go like this, or we can move like this and then go up like this, or we can go to any level and move like this. So, like this we can move, or we can go like this, or we can go like this, but these extremals will have then corners appearing here, here, and all these points corners will appear, and so y prime will be discontinuous. So, this is an instance, this is an example where this functional attains minimum value only on the extremals which are having discontinuities in the derivatives, that is they have corners in the domain. So, I mean here such functionals can occur in practice, that where the extremals will be continuous, but their derivatives will be discontinuous. So, they will have corners at a certain number of points. So, like this we have that naturally these kind of functionals occur in practical problems. Now, we will move on to the cases where we should have certain conditions derived. So, that it is ensured that if those conditions are satisfied, then the extremals where we have the value of first variation equal to 0. So, on that extremal it is a candidate for optimizing the functional, but whether it minimizes or maximizes, that is to be checked, like we check it in case of functions, the derivatives, higher order derivatives, and check whether the higher order double derivative is positive, then we have minimum. If double derivative is negative, then second derivative is negative, then we have maximum. So, like that we will recall that. So, we will actually now consider sufficient conditions for an extremum. So, here in the case of function, a function f from x 1 to x 2 into R and sufficiently smooth, then we see that at any point, interior point for an interior point x in x 1 to x 2, we express f of x plus h by Taylor series as f of x plus f prime at x, x minus h plus f double prime at x upon factorial 2 x minus h square and so on. So, here we see that if it has maximum, let us say the case when this x 1 is here, x 2 is here and x is here. So, suppose that the function has minimum. So, it should go like this, and therefore, for minimum. So, here f x can be expressed as this Taylor series if it is assumed to be sufficiently smooth, then equal to f x plus f prime x, x minus h, f double prime x upon factorial 2 x minus h square and so on. And then we see that at this point x 2, at x 2 f of x must be less than must be greater than equal to f at x 2 in certain in x 2 minus epsilon to x 2 plus epsilon. Epsilon is sufficiently small enough, and so we see that f of x plus h minus f of x equal to actually f prime at x to x minus h plus f double prime x upon factorial 2 x minus h square and so on. Now, if f prime x is not 0, then f of x plus h minus, then the sign of this is same thing as sign of this term. So, if this and say f prime at x is positive, then the sign of this is same thing as sign of x minus h. If f prime at x is negative, then the sign of f of x plus h minus f of x equal to sign of minus sign of x minus h. Now, if we take x to be in the left and the next time we take x on the right of h, then we see that this sign changes, and therefore, this in this case. So, taking x on the left and next time on the right of x equal to h, at right of x 0 equal to x h, we see that the sign is changed. Hence, f cannot have local minimum in this case. So, therefore, hence f prime x must be 0 necessarily. So, this is a necessary condition. So, likewise in our case in the functional case we saw that the first variation. So, here the derivative like first derivative is behaves like our first variation behaves like first derivative in the case of function, and for the now here in this case. So, necessary condition, if this is satisfied, then the sign of f of x plus h minus f of x is then equal to sign of f double prime x. So, if f double prime is positive, then we have minimum. So, if f double prime x is positive, we have minimum. If f double prime x is negative, then we have maximum, because in this case then you should have the situation like this. In the case of maximum, the function should be like this at x 1 x. Let us say this is x 3, this is x 3. So, x 3 minus like x 1 x 2 are the interval boundary points of the interval, and x 3 is an interior point. So, that is what should happen here. And in the case of minimum, you should have f double prime at x positive and f double prime at. So, here we should actually have this okay. Let us write it as okay, that is okay, x 3 h. So, here okay. And so, in this case, if f double prime is also 0, then we see that we have to go to higher order derivatives to check the sign of f of x plus h minus f of x. So, in the same manner, for the functional we will have to go to higher order variations in this case. Now, also we have seen that we first solve this f prime equal to 0, and the solution of this equation are those roots of this equation are the points which are called critical points, because at those interior points only minimum or maximum can occur, and therefore, of course, leaving the boundary points, because we are taking only the interior points here. So, same manner we for the functionals, if we consider I y equal to x 1 to x 2 f of x y x and y prime x. So, we see that like the points here of this equation, the extremals of the equation should be. So, the extremals are the solutions of Euler's equation which is obtained which is a necessary condition, which is a necessary condition so that this first variation delta I y equal to 0. So, this delta I y equal to 0, we have got that this implies that f y minus d by dx of f y prime equal to 0, that is our Euler's equation. And so, here the solutions solution of this Euler's equation, let us call it IE. In short, we will call it EE. Are two parameter family of curves given by y equal to y x c1 c2. Now, here what we do, we assume that this point, one of the points let us say is fixed. If these extremals are passing through a given point, given fixed point, then one of the constants, these constants C1 and C2 is determined, and we get a one parameter family y equal to y x c of extremals. Now, we consider various notions of fields of extremals. So, fields of extremals so we say that, so if certain domain D like these extremals are occurring like this, and this is domain D, or if in a region D the extremals do not intersect, then we call this a proper field. So, if there is a point where two extremals cross, then such a field will not be a proper field. So, this is the definition of proper field. If in a region D the extremals intersect all the extremals intersect at only one point, then it is called, then it is not a proper field, but it is called a central field. And the point of intersection is called the center of the field. Like for example, here it could be like straight lines passing through this point. So, they form, of course, this whole region D must be covered by the extremals, and so this is a central field. So, for example, the practical example, if you take this y equal to, let us say for example, y equal to C x is 17.2. So, y equal to C x. So, you have this from this origin all these straight lines going. So, any region containing this, so any region containing the whole, this is called a central field. So, this is an example of central field, and if you take y equal to C sin x, then we see that here this also, when c equal to 0, we get, let us say this is 0 0 and here this is 0 pi. So, all these things will be there. So, if we so in that field we should avoid this pi 0 pi. So, any region containing this one. So, like that on the left hand side also you will have this going there. So, any region like this where we avoid this pi and minus pi, we will have the central field, and 0 is going to be its center. But if pi is also included in that, then it is neither a central field nor a proper field. So, here we will have like this 0 less than x less than some number x 2. So, this x 2 must be less than pi. If x 2 is greater than pi, then not a central field. So, like this we need the notions of these proper fields and central fields. Now, we consider the family of these extremals like this. So, we have this I y, which is x 1 to x 2 f of x y x and y prime x dx. So, we consider here this I y on extremals only. As before, we had considered only on the extremals, because and this extremal should be an interior extremal, like in this case this one, it should not be a boundary extremal. Like we have in the case of function, the critical points are, all those critical points are exterior interior points, not the boundary points. Boundary points minimum and maximum can occur in other ways also. So, we consider that functional on the extremals only, and here the point A, we assume that this point A x 1 y 1 is the center of the central field of extremals. That is, we have this picture that the point A, this is x 1 y 1, and so from here various extremals are passing, and so this extremal which passes through this point A and B, that is x 2 y 2, this forms a central field, and this extremal, that is y x c, we will call this given extremal as y x equal to. So, this y x equal to y x c 0. So, fixed value given to the constant c to obtain this extremal, and when we change the c, we get all the different extremals. So, and so we assume that this is a central field, and the point A is the center of this field. Now, we need to see that the sufficient conditions are to be satisfied, we will obtain from this, so that the extremal is so that the functional is extremized on this functional, and we know whether it is a minimum or maximum value if that sufficient condition is satisfied. Now, we consider here the envelope of this family of extremals. So, here if at all it has an envelope, the envelope of the extremals y equal to y x c is obtained by eliminating c from these two equations, that y x c is and equal to 0, and del y by, so eliminating by y, sorry, this y equal to y x c, and this del y by del c at x c, this should be 0. So, eliminating c from this the curve, we get the envelope like this. So, we have the following situation here, this A, which is x 1 y 1, and here like this A will also be on, because we know that here at A, see A is passing through all the extremals. So, that means A x 1 c 0 is this point, and so here we see that del y by del c at x 1, because this, since y x c passes through A x 1 y 1 for all c, that means this y x 1 c is constant, that is y 2, that is equal to y 2, and therefore, here we see that del y by del c at x 1 c will be then 0, and so this A x 1 y 1 is on the envelope. Now, other points will be obtained like this. You have this extremal which is getting reflected here like this, because this envelope should go tangentially to these members. So, this is the envelope obtained here in this manner, and B could be here, or B can be on the other side here, and the point here, this point is called conjugate point of A. So, C 1, and this will be A star of C 2, and so on. So, the point the point A star C is on an extremal y equal to y x c and on the envelope is called the conjugate point of A, like this. So, here we see that if we are considering central field. So, if the point B is before this arc A to A star, if B is somewhere here, then we can consider the central field in a domain like this. If B is on the other side, if B is somewhere here, then obviously, we see that the extremals intersect here and therefore, it will not form a central field. So, if B, that is x 2 y 2 lies on the arc A star C, then we have a central field locally at the center A x 1 y 1 containing the point B, that is x 2 y 2. So, here you see that in this case, if B is here, we can consider this central field like this and this B will be included in that. On the other hand, if B x 2 y 2 lies on, or rather this, if this conjugate point A star C lies on the arc A star C, then the extremals intersect in the neighborhood of B, hence we do not get a central field. Thus, the sufficient condition for the existence of a central field at A, that is x 1 y 1 containing B x 2 y 2 is that B must lie on A star C on the arc this is called, this condition is called the Jacobi condition. Now, mathematically this can be seen that it can be seen that since here we get that since y x c satisfies Euler, that is f y, which is x y x c y prime x c minus d by dx of f y prime at x y x c y prime x c equal to 0. Differentiating with respect to, so let us say this is 17.4, differentiating 17.4 with respect to c, we get f y y, we will not write these dependence here, f y y and then y prime with respect to c. So, that is del y by del c plus f y y prime del y prime del 2. So, this is with respect to x, and so we get another one with respect to c. So, del x del c minus d by dx of here f y prime y and del y by del c plus f y prime del 2 y by del x del c equal to 0. Here we have used the convention that f xi eta is del 2 f over del xi del eta, that is first we are differentiating with respect to xi and then eta rather than other way around. If it is eta xi, usually books might follow in the other way around, but we will follow this convention that f xi eta, which is actually equal to del 2 f del xi del eta, means we are first differentiating it with respect to xi and then with respect to eta. So, that is del over del eta of del f over del xi. So, that is the convention we are following here in the notation. And so, let this del y over del c of x c be denoted as u, then we get here in this equation f y y u plus f y y prime u x minus d by dx of f y prime y u plus f y prime u x. Now, here there is no c derivative appearing, since in the above equation no derivative with respect to C is appearing explicitly, although it is denoting u, it is C derivative appearing there, but not explicitly. So, we have thus we denote this u x as u prime. Prime means with respect to x, keeping other variables fixed. We get we denote which gives finally f y y minus d by dx of f y y prime u minus d by dx of f y prime u prime. So, this is called Jacobi equation. This is 17.5. Is called Jacobi's equation, and we solve this, we solve 17 point, this is second order equation in u, we solve this 17.5 for u, u clearly u at x 1 y 1, that is at a is 0, if u is not 0 in the interval, x 1 less than x 2, then the Jacobi condition is satisfied. And so, we need to solve just this equation here. So, mathematically that whatever was explained here, that the extremal, that point B should be before this conjugate point of the extremal, that conjugate point of A, and so we see that u is 0 at A, and then subsequently u should not be 0 anywhere in that interval. So, that before this the extremal will not touch the envelope, and so that is what we will see in various examples in the next lecture. Thank you very much for paying attention.